Lecture 9, Part A, on rotational motion. Recall we talked about motion diagrams in the beginning of the semester. These two motion diagrams we saw before. One of a skier, whose displacement is increasing and the direction is changing. So in this type of motion, we see the skier is gaining speed and changing direction. We now can deal with this after the material of the previous week. The skier is changing speed, which requires a force in the direction or against the direction of their motion. So at first the skier is slowing down, so there's a force against the direction of the skier's motion. And the skier is picking up speed, so there's a force from gravity in the direction of the skier's motion to gain the speed. And the skier is changing directions. From the force of the snow on the skier is able to change directions. So we have a force in components with or against the skier to change the speed, and a force to change the direction of the skier, a force perpendicular to the motion of the skier, involved with just changing the direction. From the last chapter, from the last material, the last lecture, Lecture 8, we know that force, perpendicular to the direction of the motion while the skier is curving, is a force that's related to mv squared over r. The bottom figure we've also seen before. The figure skater is going up and down, losing speed on our way up, gaining speed on our way down, and moving from right to left. We can deal with all those motions, but we can't deal with the motion of the skier rotating about herself until now. And that is the topic of today's lecture, the skier's rotational motion. Another way to say it is we're not going to talk about the object, the skier, the figure skater, or any object anymore as just a particle. But we'll talk about the shape of the object. How do we make an object rotate? We need a rotational force, which will change the rotational motion. Recall that a force is not involved with motion. A force changes motion. Just as a rotational force is not involved with rotational motion, rotational force changes motion. Forces speed up, slow down, or change direction of objects, as we just saw. Rotational forces make an object rotate faster or slower, or change the direction of rotation. Looking here at an overhead view from your text of a door. The door is attached to the hinge. The door rotates about the hinge, which we call the pivot point. We have four forces being applied to this door. Force 1 is far away from the hinge. If you push on our door far away from the hinge, perpendicular to the surface of the door, you can make the door rotate. Whether it's a push or a pull to open or close the door, it's effective to make the door change its rotation from no rotation to some rotation. F2 is a force pushing the door into the hinge. The opposite of F2 would be a force on a door pulling it away from the hinge. This type of force does not involve the rotation of the door, changing the rotation of the door. F3 is similar to F1 and F2. A component of F3 is perpendicular to the door. A component of F3 is also parallel to the surface of the door, similar to F2. So F3 has a component similar to F1 to change the rotation of the door. F3 has a component opposite the direction of F2 to pull the door away from the hinge. Only the component of F3 that's perpendicular to the door, in the same direction as F1, is involved with changing the rotation of the door, whether to slow down the door as it's rotating or speed up the door as it's rotating. F4 is in the same direction as F1, in the same direction as the perpendicular component of F3 to the door. But F4 is less effective in opening the door as F1. F4 is the same magnitude, so it's the same amount of force. But it's closer in, it's much harder to swing a door open or to prevent a door from swinging closed if you apply the force at F4 versus F1. So we see from these examples that the strength, the amount of force will change the rotation of a door to make it rotate faster or slower. Where the force is applied, such as F4 versus F1, makes a difference. And the direction of the force is important too. Try opening a door with your finger close to the hinge, such as F4, opening the door or preventing a door from closing with your finger far from the hinge as with F1 versus F4, with your finger at an angle to the door as F3, or with your finger in the direction of F2, it becomes readily apparent that F1 is the most effective rotational force. The rotational force depends on the distance to the pivot, the direction of the force being the angle to the surface of the door, and the amount of force. So why do we have door handles positioned far from the hinges rather than, say, a door handle at the center of the door or close to the hinge? For the same reason, pulling on the door handle is much easier to swing open a door when the door handle is a great distance from the hinge. It's much harder to open a door when the door handle is in the middle of the door or near the hinge. This concept of rotational force is called torque. Now, not all doors have door handles far from the hinge. A contribution from a student years ago to the bad Hollywood physics lecture is a Hobbit home is surely cooler design than your home. But why should Bilbo consider rethinking the design of his front door? Notice the door handle is in the center of his rounded door. Pulling on a door handle at the center of the rounded door, where the hinges are still at the edge, of course, will make the door harder to swing open. If you notice here, in the bottom slide, as Bilbo's opening his door, look where the door handle is on the inside, where Bilbo is actually using the door handle to open the door. The door handle on the inside of the door is at the far edge, as we're used to. This makes it, of course, much easier for Bilbo to open the door from the inside than it would from the outside. Now, apparently this is not the full story, although Hollywood can have the door handles positioned on the outside of a door in the middle as an ineffective way. It apparently is done in some locations. I was once in Spain opening up a door, and the door handle here you can see is in the middle of these very large, heavy doors. The person I was opening the door with, she was complaining how heavy the doors were to open. So I took a picture to show you that it's not just hobbit holes with their doors that have door handles in the middle. There actually are places where door handles are in the middle trying to swing open, that you use to swing open very heavy doors. Again, the door handle being far from the hinge at the edge of the door gives you effective, strong rotational force or a strong torque. Being near the middle makes it much more difficult to get the same torque to swing open a door. So the concept of how a force is applied and how it affects the rotation is called torque. The greater distance from the axis of rotation a force is applied, the greater the torque. So it's not just about the door handles and pulling on doors. Torque is involved with the rotation of all objects. Instead of a door, the long rod could be the bones of your upper arm. The bones of your upper arm is rotated by the tendons attached to the bone that a biceps pull on. So your biceps, in a sense, are pulling on your upper arm to rotate your upper arm. Where the biceps are attached, where the tendons are attached, they're attached a distance away from the rotation point from your elbow. The stronger your biceps are, the stronger the force from your biceps on your upper arm, the greater rotation of your upper arm, the greater rotational force or torque. The greater distance the tendons are from your joint, from your elbow, from the center of rotation, the greater torque. So why is it that your tendons are not attached further from your elbow, from the center of rotation? Well, attaching the tendons farther away would make the tendons be more stretched, perhaps reducing their strength, and be more exposed to harm. But a chimpanzee and other creatures do have their biceps and their tendons from the biceps attached at a greater distance from the center of rotation, a greater distance from their joints, a greater distance from the elbow than do people. That's one reason that the chimp's arms are always more in a contracted position, an angled position, compared to our arms being straight. Their tendons are farther away from their elbow. Because of that, they have a much greater rotational force, so that the bicep being attached farther up the upper arm gives them a greater torque, which makes the chimp easier to rotate its arms, to greater strength to pull itself, swing, and throw things. So torque, we know, is due to the component of the force perpendicular to the radial line. The force that's perpendicular to the surface of the door, or the force of the tendon perpendicular to the upper arm. Here in the illustration from your text, we have a force applied to a wrench, which is making the wrench rotate about the pivot shown in the illustration. The force on the wrench has a component of force perpendicular to the length of the wrench, designated by the position vector r, from the pivot, the center of rotation, from the center of the nut, to the arrowhead, the position vector pointing to the force. The force perpendicular to the position vector is the one that's related to the rotation of the wrench. It's the one that's related to the torque. So the product of the distance, the position vector r, from force to pivot, times it by the perpendicular force is our torque. But what is that perpendicular force? The component of the force that's perpendicular to the position vector? Well, we see that F perpendicular is equal to F sine phi. It's the component opposite phi, the angle between the force and the position vector. So torque is distance r, the position of the force from the pivot, the amount of force F, and the angle between r and F, the angle between the position vector and the force vector, by the sine function. When the force is parallel, phi is 0 and sine of 0 is 0. When the force is perpendicular, phi is pi over 2 and sine of pi over 2 is 1, the maximum amount of torque you can have from the angle. We can interpret torque in another way. Rf sine phi, we can rewrite Rf sine phi as R sine phi times F, or F times R sine phi, meaning that R sine phi is just as good as F sine phi. R sine phi would be the component of the position vector perpendicular to the force, rather than the component of the force perpendicular to the position vector. Whether it's R sine phi times F or F sine phi times R, we get the same result. The position vector r and its component r perpendicular to the force, also called the line of action. The r perpendicular to this force is opposite the angle phi, so r perpendicular is related to r by r sine phi. It's more common to use the f sine phi, the f perpendicular component, the position vector, but you can just as well use the component of the position vector perpendicular to the force. Either way, we're talking about the force perpendicular to the position or the position perpendicular to F. Those vectors perpendicular to each other is what is important. How do we balance torques? When we have two torques, they can increase rotation, decrease rotation, or cancel each other out. Here we see two objects, one heavy, one light, sitting on a rod, but they are balanced on a pivot or a fulcrum. The heavy weight of the cow is creating a torque to the left of the fulcrum. The very light weight of the bunny is creating an equal torque far away from the fulcrum on the right. If the seesaw is balanced, the teeter-totter is balanced, then the torques of this are equal. The cow creates a torque to make the seesaw rotate or flip, if the bunny wasn't there, counterclockwise. The bunny creates a clockwise torque, which would make the rod rotate in the same direction as the clock. The force on the rod, the force on the seesaw from the cow is much greater, the weight of the cow versus the weight of the bunny. But the torques will be the same. If the weight of the cow is, let's say, 100 times the weight of the bunny, then the distance the cow is from the pivot, from the fulcrum, from the balance point, will be 100 times closer. Thus the torques equal. Force times distance times sine theta. In this case, the force is perpendicular to the seesaw, so sine theta is 1. So the force is the weight of the cow. The distance is from cow to pivot. So weight of the cow to the pivot point is the torque of the cow. The much lighter weight of the bunny is at a much greater distance to the pivot point. So if the bunny is 100 times lighter, it sits 100 times farther to get the same torque, 100 times the distance from 100th of the force. If we move the pivot point and the cow is farther away, then we simply have to increase the amount of force on the other end, increasing the amount of bunnies, balancing the torque. This idea of having forces a good distance away from a pivot to balance or create larger forces closer into the pivot on the other side is the idea of leverage. The distance of force applied from a rotation is called a lever arm. So here, the girl is lifting up the car by using a 25 centimeter lever arm, or using the leverage of 25 centimeters, applying a 50 Newton force. So the girl is pushing down with 50 newtons, 25 centimeters from the rotation, the center of rotation, to be able to lift up a car with a force of 5,000 newtons. 5,000 newtons is 100 times the force of 50 newtons. Therefore, the force of 5,000 newtons has to be applied 100 times closer. For a force of 5,000 newtons 100 times greater, the distance must be 100 times less. 100th of 25 centimeters, or 0.25. So again, she applies a small force, a big distance, which is equivalent to a torque on the other side, the torque lifting the car, of a big force, an equivalently smaller distance. 50 times 25 is the same thing as 5,000 times 0.25. This idea of leverage, applying a small force, a big distance from a pivot point, to create a much greater force a small distance away to lift objects, is called leverage. The first person we know to describe this mathematically in a useful way is Archimedes. Archimedes has a quotation, "Give me a place to stand and I will move the earth," meaning an ordinary human force applied to a long enough lever arm can lift anything. An ordinary human force, a good distance away from a pivot point, can create enough force a very close distance to the other side of the pivot point to lift any weight you can choose. If we have balanced forces or balanced torques, so the object is not changing its rotation, such as the cows and the bunny, this would be an example of static equilibrium, or static rotational equilibrium. Let's do an example. A 2-meter long board, shown below, which weighs 50 newtons, extends out over the edge of a table. The triangle, the pivot, or the fulcrum, labeled edge beneath the board in the drawing, represents the edge of the table. But 40% of the board's length is off the table. Therefore, 60% of the board's length to the left of the edge is over the table. How far beyond the table edge can a 25 Newton cat walk before the board begins to tilt over the edge of the table? The weight of the cat and the weight of the board are two forces creating torques on this board. If the board is to remain balanced, the cat finds the farthest position, the greatest distance it can sit from the edge, to keep the balanced torques on the board to prevent the board from rotating. The center of mass of the board is at 1 meter. This is where the weight of the board is modeled to be. The force of the earth pulls down halfway in the middle of this uniform length board. So the center of mass is a distance from the edge. The center of mass is 10% the length of the overall length of the board, 10% the length from the edge, the table edge, to where the force of the earth, the weight of the board, is operating. Because the center of mass is halfway, or 50% the length, and the edge is at 60% the length of the board, and the force of the earth is acting a distance of 10% of the length of the board. This is creating a torque that would flip the board in a direction counterclockwise. This must be balanced by a clockwise torque from where the cat sits, which we are to find, the distance from the cat to the pivot, and the weight of the cat. We know the weight of the cat is half the weight of the board, 25 newtons versus 50 newtons. So if the cat weighs half the amount of the board, then the torque of the cat, coming from half the weight, the cat must be sitting at twice the distance if it weighs half as much, twice the distance from the pivot, to create the same clockwise torque as the counterclockwise torque from the twice as heavy center of mass of the board, which is twice as close. Let's see that in an equation. The torque of the earth on the board, the weight of the board acting at the center of mass, is equal to the torque of the cat on the board, counterclockwise versus a clockwise torque. The torque of the earth on the board is the force of the earth on the board, acting at the center of mass, or the weight of the board acting at the center of the mass. The distance of COM, center of mass, to pivot, is the torque of the earth on the board, or the weight. The force of the cat on the board, or the weight of the cat on the board, is sitting some distance away from the pivot point, the edge to where the cat is. Those are our two torques. Those are our force times distances. The product of those equal each other. It's a case of balanced torque static equilibrium. We know the weight is 50 newtons of the board. The distance the board is from the pivot point is 10% of L. The weight of the cat is 25 newtons. The distance from cat to pivot is what we're solving for. We can play with our numbers and plug in C, that we get the cat to be sitting twice as far as the center of mass is from the other side of the edge. Guess the cat is half his weight. Work out the numbers and see you get the same result. Submit your answer submit your answer to the solution of this question on Blackboard. Again, rotational force, or torque, is about a change of rotational motion. So when we're changing rotational motion, we're making something rotate faster or slower from the application of a torque, a rotational force. Angular acceleration, or alpha, the change in angular velocity, or omega, in time, is what an angular acceleration is. So we're making something rotate faster and slower by applying a rotational force. Applying a torque makes something change its rotational speed. Therefore, applying a torque involves a rotational acceleration or an angular acceleration, the alpha, from the last unit, from the last chapter. Again, recall this picture from the last lecture, the last chapter. The wheel is rotating ever faster. Omega initial is less than omega final. Its rotation is picking up. So that's an angular acceleration. It's rotating faster. How do we get that to happen? We must push on the wheel. We must push in a direction perpendicular to the spokes, tangential to the rim of the wheel, to make the wheel rotate faster. That force perpendicular to the spokes is a force perpendicular to, in a sense, the lever arm. That force perpendicular or tangential to the rim is the torque, which is making the wheel rotate. So if I apply a force in a direction tangential to the rim of the wheel, so the wheel rotates counterclockwise, then I've created a counterclockwise torque, which is making the wheel rotate ever faster counterclockwise, or I have an acceleration, an angular acceleration, counterclockwise from the counterclockwise torque. Recall from the last chapter, in the last lecture, we can relate linear motion to circular motion, distance to angular distance, position to angular position, x to theta, for example. Linear velocity to angular velocity, v to omega. And now acceleration to angular acceleration, alpha. These clockwise and counterclockwise directions of rotation and of alpha and torque are vectors. They actually have directions beyond just saying clockwise and counterclockwise. By convention, an object that is rotating in the way that your right hand curls when in an ordinary position looking from above your right hand, as in the drawing. The fingers of your right hand, if they curl in the direction counterclockwise and your thumb is pointing up, then your counterclockwise curl of your fingers in your right hand with your thumb pointing up, is the direction of omega. Omega counterclockwise is actually in the direction by convention of your thumb pointing up, as we see in that illustration. So omega is pointing up or in the positive direction when a disk or a wheel or an object is rotating counterclockwise. If the object rotates clockwise, then your fingers, you curl clockwise and your thumb points down. This is the direction, this is how we find the direction of omega. It is similar to tightening a screw or loosening a screw, tightening an object or loosening an object. When you tighten the object, you rotate your hands clockwise and your thumb points in the direction the screw goes. When you loosen a screw, you're rotating the screw, your fingers point counterclockwise and your thumb points out the direction of the screw. To loosen the screw, it starts coming out, and so a counterclockwise rotation follows the direction outwards that your thumb is pointing, and the screw would rotate and come out. How do we get this to happen? We apply a force, such in the bottom illustration. We apply a force counterclockwise to create a torque to change the rotation. So applying a force counterclockwise creates or changes rotation in the counterclockwise direction. So I take an object and apply the forces in the bottom of the illustration, it'll start rotating counterclockwise. I curl my fingers counterclockwise, my thumb points out in the direction of the changed omega, direction of the changed rotation, a counterclockwise change in rotation, therefore a counterclockwise alpha and a counterclockwise torque. This is a vector product. Newton's second law for rotation is alpha, rotational acceleration, relates to rotational force torque divided by I, where I is the moment of inertia, or the rotational mass, or rotational inertia. Moment is the Greek word, stems from the Greek word where momentum comes from. It's about motion, the motion inertia, or the rotational inertia. So objects with greater rotational inertia, larger values, magnitudes of I, greater moments of inertia are harder to get rotating. For instance, between A and B, the mother is rotating her 3 kids on the merry-go-round. If the 3 kids sit at the far edges of the merry-go-round, it's hard to get the merry-go-round rotating. If the kids sit closer in, it's easier to get the merry-go-round to rotate and easier to stop the merry-go-round from rotating. Where the kids sit makes it more difficult or easier for a force to increase or decrease a rotation. So where the masses are applied, the kids, affects the difficulty of changing something's rotation. Recall mass is inertia, just as your brother, say, or your friend or your sibling may sit on the couch all day. They have a lot of inertia to get them moving. Mass is an inertia, the reluctancy of an object to change its motion, to speed it up or slow it down. I, the moment of inertia, the rotational inertia, is the reluctancy or the difficulty of an object to change its rotation, to make it rotate faster or slow down its rotation. So we see here as the mother is applying a force tangent to the merry-go-round, the circle of the merry-go-round, the circumference, applying a force perpendicular to the direction from her to the center of the merry-go-round. So the mother is applying a force which is creating a torque on the merry-go-round. Although she may be applying the same torque in A and B, the effect of the torque is greater in B when the masses are closer in towards the center of rotation. That's when I is small. Where the masses are, the kids sitting closer in, is a small value of I. Our equation for moment of inertia, rotational mass, I, is the sum, sigma, of the amount of masses, in this case the 3 kids, and where the 3 kids are sitting. R squared is not the radius of the merry-go-round. It's not the radius of any shape. R squared is the distance from where the kids are to the pivot point, the center of rotation, the center of the merry-go-round. So if the kids are sitting 10 times as far away in A as they are in B, then 10 times R is what we would square, and I equals m times 10 times the value of R squared. So I would be 100 times as great in A if the kids are sitting 10 times farther away. The rotational inertia, the moment of inertia in A, therefore, would be 100 times greater or more difficult to get rotating in A by a factor of 100. Another example is if all the mass is on the rim versus at the center between these two pictures, we have a smaller moment of inertia when all the mass is close to the center, or greater moment of inertia when all the mass is at the rim. And it's much greater when all the mass is at the rim versus at the center, because the moment of inertia depends on where the mass is distributed, the square of the distance of where it's distributed. We'll talk more about moments of inertia in Lecture B. To sum up, we know force is related to rotational force, or torque now. Mass is related to rotational mass, or the moment of inertia I. Acceleration is similar to, related to, angular acceleration, or alpha. Newton's second law of acceleration is force per mass, net force per mass, has a rotational analog of alpha. Angular acceleration is related to the net rotational force, the torque, divided by the rotational mass, the moment of inertia. We'll explore more of a moment of inertia and center of masses in lecture and energy of rotation in part B of Lecture 9.